Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com.
That's ProfSam.com.
Today we're taking a deep dive into electron emission from Unit 11, Dual Nature of Radiation and Matter.
And the goal is to make it super simple.
Yes, so simple and, exam safe that you'll lose any fear of it and remember the physics for life. So let's start with a question that feels a bit contradictory. We all know that electricity flows because metals are just full of these free electrons, right?
Yes, that's the whole definition of a conductor. These electrons are delocalized, they're free to move all over the crystal lattice.
Exactly. But here's the puzzle. If these electrons are already free and they're moving incredibly fast inside the wire,
And they do have a lot of kinetic energy.
a tremendous amount.
Yeah.
So why don't they just, fly out into the air or into a vacuum? Why, when they reach the surface, do they just stop?
That is a good question. They're free to move within the wire, but it seems like they're trapped by the wire.
Precisely. And this leads us to a really surprising piece of technology. Think about old radios or even modern X-ray machines. They all use something called a vacuum tube.
Ah, yes, those glass bulbs that glow inside. Usually there's a filament that's white hot.
That's the key right there, the white hot part. To get a stream of electrons, which these devices need, we have to heat a metal filament so hot, sometimes 2,500 Kelvin, until it glows. Only then do electrons start popping out.
Wait, hold on. You're already running a huge electric current through the wire to heat it up. Shouldn't that electric field be enough to just pull the free electrons out?
You'd think so.
Why do you need to heat it? Why is temperature the magic ingredient here?
And that mystery.
Yeah.
That's our gateway into the whole concept of electron emission.
Okay.
Let's unpack this. So the core idea is that even though we call them free, the electrons are actually trapped inside the metal
Trapped by what, though?
by electrical forces.
Yeah.
The metal lattice is made of positive ions, right? And the electrons are negative. So there's this massive overall attractive pull.
Ah, I see. So an electron can move freely among the ions, but the moment it tries to leave, the whole chunk of metal becomes positively charged and just yanks it back in.
You've got it. Let's use an analogy. Imagine the electrons are like car attendants working in a very deep valley.
Yeah.
The metal is the valley.
Okay. A valley parking lot.
Exactly. And the steep walls of this valley,
Hmm.
that's the potential barrier. It's the collective pull of all those positive ions at the surface.
Right. And to get out of the valley, you have to climb the wall.
Precisely. Now, if an electron wants to escape, to drive up the mountain into free space, it needs enough energy to climb that wall. The minimum energy it needs to get to go over the top. That's what we call the work function of the metal.
The work function. And it's denoted by phi naught, feet of dollars.
Yes, feet of dollars. So this work function is basically the energy price for an electron to escape the surface.
Yeah.
And this energy has to be supplied from outside, right?
It has to be, yes.
Good.
Yeah.
Now, let us see how NSERC gives the official definition. Could you read that for us?
Of course. It says, this minimum energy required by an electron to escape from the metal surface is called the work function of the metal. It is generally denoted by 50 dollars and measured in EV, electron volt.
Perfect. And that unit, the electron volt or EV, is really important for exams. It's tiny.
So how do we supply this energy? You mentioned heat. Are there other ways?
Yes, there are three main ways. The first one, as we discussed, is thermionic emission.
Thermo, meaning heat.
Right. You heat the metal, the electrons get a lot of thermal energy, they start jiggling around violently, and some get lucky enough to have enough energy to jump over that barrier.
Okay, that makes sense. Like heating the valley makes the attendants restless, and some manage to scramble out.
That's the analogy, and the effect is dramatic. Let's take a quick example. For a tungsten filament, if you increase the temperature from 2,000 K to 2,500 K,
That's a 25% increase.
just a 25% increase. But the thermionic current, the number of electrons escaping it, increases by over 280 times.
Wow. 280 times? That's not linear at all. It's exponential.
It is exponential. It's because when you heat it, the tail end of the energy distribution curve, the few electrons with super high energy,
Oh,
that tail grows exponentially, and those are the ones that can escape.
I see. So a small temperature change unleashes a flood.
Exactly. Okay, so the second method is called field emission,
Field, as in electric field.
a very, very strong one. We're talking on the order of 180 volts per meter. You basically apply such a strong field that it just rips the electrons out of the metal.
That sounds quite forceful.
It is.
Yeah.
But the physics is even cooler. The field doesn't just pull the electron over the wall. It actually distorts the wall itself. It makes the barrier thinner
Thinner. How does that help?
because of quantum mechanics. The electron can do something called tunneling. It can pass straight through the barrier, even if it doesn't have the energy to go over it.
So it's not climbing the value wall. It's like the field pushes the wall in so much that the electron can just phase through
Perfect way to put it.
it.
And that brings us to the third and most famous mechanism, photoelectric emission.
Ah, the one Einstein got his Nobel Prize for.
The very same. This is where light comes in. If you shine light of a suitable frequency onto a metal surface, electrons get knocked out. We call them photoelectrons.
So the light itself provides the energy to overcome the work function.
Yes. The analogy here is that the light comes in little packets of energy, photons, like invisible hammers. One hammer strike, one electron knocked out.
A direct hit.
A direct one-to-one interaction. And this is what we'll explore next in this unit, because this effect is what proved that light is made of particles. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is PROFSAM.com. Okay, now let's talk about some common mistakes. Exam-killing misconceptions that trip up a lot of students.
The silent killers. Yes, please. What should we watch out for?
Misconception number 1. Thermionic emission is basically the same as photoelectric emission, just with a different energy source.
I can see why someone would think that. In both cases, an electron gets energy and escapes. The end result's the same.
Exactly. But it's a completely wrong idea. The physics is fundamentally different. The correct idea is that thermionic emission is probabilistic. It's about random heat fluctuations. An electron needs luck.
It needs to be in the right place at the right time to gather enough random thermal energy.
Yes. Whereas photoelectric emission is deterministic. It's a single, targeted photon strike. If that one photon has enough energy, the electron escapes instantly. If not, nothing happens.
So one is like winning a lottery, and the other is like using a key to open a lock.
What a great way to put it. Remember that. Thermionic is dice roll. Photoelectric is a key.
Got it.
Okay, misconception 2. This one is about light. More intense light means more energy, so intensity should be the main thing for the photoelectric effect.
This is what classical wave theory would suggest. No, a bigger wave carries more energy.
It does, and that's why it was such a puzzle. But the experiments show the correct idea is that there's a sharp threshold frequency. A minimum frequency, let's call it a cutoff point, a hard cutoff. If your light's frequency is below that threshold, nothing happens. I don't care if you use a light as bright as the sun, no electrons will be emitted.
So frequency is the deciding factor, not brightness.
Yes. Frequency is the gatekeeper. Intensity only decides the flow. How many electrons come out per second, but only if the gate is already open.
So frequency is the gate, intensity is the flow. I'll remember that.
Perfect. And the last one, misconception 3. Work function is the same for all metals.
People might think it's a universal constant, like Planck's constant or something.
They do. But it's wrong. The work function, C(T)(Y), is a material property. It's like a fingerprint for each metal.
So different metals hold on to their electrons with different strength?
Exactly. Platinum holds on very tightly. Its work function is high, about 5.6 eV. It's a high cliff to climb. But sodium lets go very easily. Its work function is just 2.3 eV, a very low cliff.
So work function is a material fingerprint, not a universal law.
You've got it. Okay, so to help all this stick for exam day, let's lock in some memory anchors.
Yes, please. Mnemonics are always helpful.
First, simple phrase to cover it all. 3 ways out. Heat up, photon knock, field tunnel. Work function is the wall.
Heat up for thermionic, photon knock for photoelectric, field tunnel for field emission. Simple and effective.
Next, a physical gesture. When you're studying for thermionic, just rub your hands together really fast to feel the heat. For photoelectric, make a sharp, striking motion with your hand, like a photon hitting something.
And for field emission?
For field emission, push down on an imaginary wall in front of you. That's the field deforming the barrier.
I like that. It connects the concept to a physical action.
And one last association. Think of light photons like this. Violet photons are energy assassins, and red photons are energy weaklings. A single high-energy violet assassin can knock an electron out, but a million low-energy red weaklings can't do a thing. That's why UV light causes sunburn. It's a photoelectric effect on your DNA.
While red light doesn't. Because it's about the energy per particle, not the total number of particles.
Now you're thinking like a quantum physicist. Okay, let's summarize this whole thing in 3 key points for your exams. First, the minimum energy an electron needs to escape a metal surface is called the work function. It's a unique property for each material and is measured in eV.
Point 1, check.
Second, the 3 main ways to provide this energy are thermionic emission from heating, photoelectric emission from light of a suitable frequency, and field emission from a very strong electric field.
The three mechanisms. Got it.
And third, and this is the big one, photoelectric emission proves light's particle nature because it depends on a threshold frequency, below which no emission happens, no matter how intense the light is.
And that observation simply cannot be explained by wave theory.
It cannot. It's pure quantum mechanics. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROFSam, right?
Yes, ProfSam.com. Good luck with your studies, and keep diving deep into physics concepts.